Still recording, right? Now zoom share to kori ni amra. Zoom share ta korte হবে, right? তো এই zoom টা বন্ধ হয়ে গেল আবার। আচ্ছা, share. Share. That's fine. আচ্ছা ঠিক আছে, এটা বিষয়। স্যার এটাকে করেছো তুমি? এটাকে অল্প can you see this thing? Yeah, this screen is visible, right? Is that free there? What screen is this?
So what do you think? Last time we do it. Let's start the session after the break. Our next speaker is Professor Debraj. He did PhD in 2013 from Washington State University. Then he was 3 years HRI. Means all and overlap that time. Then he was postdoc at University of Warsaw, Poland, followed by postdoc in Barcelona. Then he was assistant professor at YouTube for quite some time, and then he joined HRI as a professor. So, thanks to the organizers for inviting. And it's very nice that the campus is very beautiful. So I talk. So this is actually the group from HRI, and there is past and present. You can say it's a quite large group, and you can see all these organizers are also here itself. Yes. And so today I will talk about quantum critical sensors, but there is also a multi-critical sensor. If I get time, I guess that I will get time. But if I get time, then I will go to quantum multi-critical sensors. So my can you listen to me? Okay, so
now it will. Now it will.
Connect was no, we have removed it, right?
Which isn't it this one? What about the other laptop? This laptop? कहाँ गया ये जो यहाँ पे था ना ये वाला कहाँ गया?
that was working.
yeah, so can you listen to me? My idea is to basically briefly talk about the basic of estimation theory. So that's the background of metrology, and I connect it with some many-body quantum physics. Okay. So there is some criticality based quantum sensing.
and then quantum sensing via localization transition. So these are the parts that I will try to spend most of the time. If I get more time, then I can go to the next parts where there is like, what is the exact resource, that's actually providing the advantage, quantum advantage at criticality, and then idea of multicritical sensing. And these are the papers. These are the two papers. All papers are related to many-body quantum sensing. But the first papers that I will focus on, and the first paper was what is done with my student, PhD student, Varun Saab. And in the second paper, there is another student who is a PhD student of Professor Ujjwal Sen, and he's also collaborator in this work. Hello. 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 Okay. So let's start with classical estimation theory first. And the aim is to about what we want to do is to find the optimal estimator. For say that we have some unknown parameter, and these x's are these are observed data. So we have to do some statistical modeling. We have to find constant the probability density. So these p's are the conventional probability. So given the value of x, what are the observed values? And then what do? We do a minimize over this mean square error. So whenever you do that, you are also doing certain things like that, right? So for example, let's say that you want to measure a temperature. So there can be different kinds of thermometers. So there can be physical thermometer or normal thermometer. You can put it under the arm, you can put it in normal. So you have to find what is the best way to find the best estimator for this measuring the temperature. And we will do in context of unknown quantity. So lambda is my unknown parameter. And there is something called mean square error. It's defined here. And for the unbiased actual estimator, it's actually a standard deviation. And this is lower bounded by the very special quantity, which is Fisher information. The definition of the Fisher information is given here. It's in terms of this probability density. Right? But now we go to this quantum thing of this classical. So in the quantum thing, we have some unknown parameter lambda, and we have to now encode it somewhere. And now we have to talk about the quantum state, which is some rho lambda. And this lambda is some self-adjoint operator actually. And this describes a quantum measurement, and then it is followed by some classical data processing. And this step variance of measuring this unknown quantity is bounded by this quantum Fisher. So this is the celebrated quantum grammar of bound. And this is this quantum Fisher information. So if I want to give a definition, then there is a definition in terms of symmetric logarithm derivative. But we are not doing that. But I am going to tell about, okay. So that means if you see this quantum Fisher information, so you have to know what is the quantum state. And experimentally finding a quantum state is very expensive. Because you have to do a lot of measurements. There is tomography and things like that. So instead, what is better that you find something through a experimentally measurable observation. That can be magnetization or some field or something like that. And then this observable, this is called observable Fisher information. What you see here on the top, the numerator, so there is this, when you change your parameter slightly,
the last slide, you said lambda is a parameter, and lambda is also a self-measured operator. So is a quantum state how?
Yeah, so in quantum mechanics, lambda unknown parameter always not an operator. It can be that you have inferred from some measurable operator. So that measurable operator can be, so this is a set of many measurable operator in quantum system. Yeah, but
It is also a parameter. How a parameter for that quantum state.
yeah, so let's say you want to measure magnetism.
Yeah.
So there is one mechanical operator for this muscle. So if you find the expectation value of quantum state based on you get that. So the other parameter is the magnetization. The operator for finding this.
Parameter is the execution value of this operator.
Yes. But the goal is that how precisely you can measure something. So you can measure anything, and there can be different ways of measuring. And then there can be different protocols that you can think of measuring. The idea is that which protocol is the best and which kind of operator is the best for this. So there is a whole estimation going. So there is a fundamental lower bound that you can reach. Let's say that you want to measure some validation. But you cannot measure it with arbitrage. That's not possible. Okay. So obviously, whenever you measure some operator, right, your expectation, so there is a standard deviation that you got, that is variance that you have. So, but then your aim is to lower this variance, and then this special information, this gives quantum special information is the lowest bound, possible bound. Now, can you reach this, or how can you? Okay. So that is the question, and this lower bound you can infer from this quantum state, right? But now think about the many watt system, requires a number of degrees. So the recursion is going very fast. So to experimentally measure this quantum state is very not trivial. And the system now having to this described by the quantum state. We have to do many experiments. So you have to think of a positive experiment, the computational which is like but then so many measurements you have to do. Or you can also think like you can think like getting this single body density matrices and this two body density correlation matrices. Through that also you can construct the state, but it's actually impossible for anyone. So then your aim is to find the observability that you can quickly, do a estimate or not so many sets of measurements, and that's what is observable feature information, and it's actually defined with this second moment. So how it's if you change the parameter a little bit, how this observable is changing, and a ratio with it the variance, the denominator. And you have to actually optimize this quantity. What you can show that if you optimize this quantity, then it is actually equal to quantum efficiency. So when you optimize to all observables, then you will get this quantum efficiency information, which is the ultimate power. And actually, there is a geometrical interpretation of this whole thing, and it's actually related to fidelity susceptibility. You have heard the last lecture of Victor. He also little bit talked about this couple of slides. And so in the states, what happens that when you look into this Fisher information, it's also parameter estimation. In the state case, it's also related to the distribution states, how far they are and things like that. And then you can go through goods distance, and actually that can be expressed in terms of this fidelity. So fidelity is just overlap, you can think overlap between two states.
How is the maximization of all possible observables done? All possible observables means a huge number of.
Yeah. So that can do.
No, that is done just randomly, whichever observable possible one by one.
Yeah, we can think about all possible observable. One observable, which is the optimal one. Okay, that will saturate. Okay, but it might be that this observable is not experimentally visible. It might be something nonlinear, or it might be something that you have to construct. So then you don't go for it. If you are thinking from a very experimental point, then you will choose some other way to this experimentalities. But here. Now the idea of critical quantum sensors. Okay, so this is actually I have summarized here, and it's so let's see that what's happening around the critical. So if you have many words quantum transition, okay, so let's say that lambda is the parameter, and this is the parameter you also want to estimate. So at the thermodynamic limit, what is happening is let's lambda c is the critical point. So if you look into this, what we have seen actually this quantification information is related with fidelity susceptibility. So if you look into the scaling of the fidelity susceptibility, so these alphas, betas, mu's, these are scaling exponents. So this shows how a physical system is behaving near criticality and how their nature of this criticality can be captured through this critical exponents. So if you little bit move away from the criticality, so this alpha is the exponent for the lambda tends to be infinity. And zeta is actually the goal. So let's say the first we have to think about the second order quantum description. And at that, then you can define something called correlation length. And this mu is controlling the divergence of this correlation length near criticality. And you see that there is a scaling exponent associated with that. There is also a finite size scaling when you are just at the criticality in the thermodynamic limit. And that let's say that this fidelity susceptibility or the quantum Fisher function that scales like L by beta. So these are the features of quantum that happens. A second kind of thing that you can do is that you can do this is also called this Prof kind of thing, or so you can write your quantum Fisher information as a function of this lambda minus lambda c. So G is some arbitrary function. What function you got? Some arbitrary function. And it's how it scales is L to the power alpha by mu. And if this, so this is finite size scaling x. So this was everything here I was talking about infinity, going to infinity, and I am talking about finite size scaling functions. So if they have two, you know, if you think simultaneously, then this parameter beta, L to the power beta, this actually has to be L to the alpha by mu. So now you see what happens if you write, if you see, then you can see that this system size asset can be a resource. So what I mean that I will create a network systems. I will see the scaling of my Fisher information of fidelity susceptibility with system size. And if I can increase my beta as much as I increase my beta, so it will give you alpha equal, let's say, something more than 1. That means I have a better sensor. So lambda is the parameter I am interested to my student, and I will just build some system which is more and more, and I will get more precision in estimating this unknown parameter by increasing the system size. My aim is to choose a system so that this beta is as large as. And so now, is there a bound? Means what? How large beta can be? So F is proportional to L. If this happens, then this is standard quantum. So this is the short noise. So this is the best you can do in classical mechanics. Okay, but not in classical mechanics. In classical physics, but still in quantum system. But quantum system, but classically, it's a program system. So if you do all combination of program states, the best you can do something that is going to be proportional to the system. Nothing more than that is possible. But if you use some other resource, for example, some quantum properties, you can be entangled. There are things beyond entanglement. Then even you may increase the picture greater than 1. Okay. And this F equal to L square is Heisenberg limit. This is called Heisenberg limit. But this is the ultimate limit. It's actually very long. But there are some in contest it can be shown that this is the ultimate limit. For example, in the context of phase estimation, where you think like you have some space theta and there's some space psi, and you are going to do minus I h theta psi, and through that you can take the psi entangled state, or you can take the psi product state and calculate all kind of initial state, product state, entangled state, optimize over that. You will see that which has a Th kind of state on the two kind of states. These kind of states which are lot of entanglement in maximal entanglement, they actually achieve this Heisenberg limit. But this is actually not a bound. Okay, I will talk about
One less than 2, or it can be less.
it can be beyond 2 as well, but the system has to be different. For example, if the system is non-linear, entanglement is non-linear, then it can be beyond. Another system where your energy is not on an extent. For example, if you are taking a many systems particle, E by L is not converged to L. For example, it can happen in star angles. You have a linear gradient. So as you go bigger systems, the energy extends, it's increasing. So that kind of system is definitely bigger. If I get time, I will show that in a non-number conjugate kind of system, I have done like one of that. It can be also better than.
So in terms of scale,
Yes. So although I am talking this next question, although I am saying that it's unknown parameter, I am not lying about. So I know I have a rough idea why it is a critical point. But I don't know with the extreme. I want to now know into the extreme. So I will prepare a state, here the critical point, then maneuver my unknown parameter, it will be around. Okay, and then I will see how things behave. And now it's time to go beyond that. So the system I will first talk about is, I propose. So I talked about second order quantum transition, but now I will talk about something which is really not second order transition, but it's a phase transition, phase transition, in localization transition. This is the system I'm talking about. So it has some interaction, some hopping term, and some quasi-periodicity. So this potential term with V, so you are seeing there is a irrational number, and this irrational number is basically a quasi-periodic. Okay. And in this system, there is an energy independent localization transition at a finite modulation strength. Okay. So this localization transition is really different from let's say that it's an insulating phase localization, but it's different from non-insulating kind of things. What happens if you are knowing our post-abort kind of model? So there is a suboptimal phase, and then you go and they get certain strengths of interaction to create small. So there is a metal, but due to interaction, it's image. So then a gap is created due to interaction. But here it's not due to interaction. Even if you do due to zero interaction, it's a little bad for it actually. So then you have you just have some randomness, quasi-randomness in form of this quasi potential, and that stops tunneling. And it's happened because you can think the position of the quasi-randomness, there are multiple scattering center, and this wave front when they propagate, they can respectively interfere. and the particle can be localized. So this is the physics of similar kind of physics like Anderson localization. Okay, and for this there is a finite value to why this localization happens, and it has no mobility. All the function will be beyond this. Okay. And when you introduce interaction actually tend to make the state more delocalized. You localize input interaction, but then you can go to little bit beyond 2. Okay. So and you can again localize it, and this will not come out with this many model localizations. So if I show real data, then let's say this is your system looks like this possibility potential, and I have a U versus V. So this is localized space. This will be localized space. You can see the structure of the wave function in the localized space. So they are highly peaked at certain lattice sites, but in the delocalized superposition, the particle can be able to start with there. The localized space particle is able that's like one. When you have multiple particles, that's all right, but they will see that this is places. So they are not coming. And so after this, now let me show this quantum Fisher information and how it scales with system size. And so this is my peak, and around 2 you can see there is a peak. And as I am increasing my system sizes, so I most only did not write what are the system sizes, but basically the peak is getting shorter and shorter. Okay. And I can look into the scaling, and I can see this quantum Fisher information is scaling as L square. That means we have actually Heisenberg scaling.
You said that G equals to 2 means energy independent localization. So this means this should be compared with U or T.
What is E?
U or
U is 0. So I am now first initially talking about when it's a single particle calculation. It's a single particle calculation. I am now talking about the non-interactive.
so if I T equals to that
Yes. So that the transition happens. So transition is exactly if I equal to 2 when you have no interaction. When you have interaction, then this transition was books it that right. Better than. Yeah, FQ is just related to something. So it depends on what's the mathematical expression. So we just know CC. So let's say that so we have come down and we see that I have a little bit. So this is my slide. And I do it square. It's proportional to this. So you basically magnetize your field. So there is definition in terms of symmetric logic derivatives, but when this parameter shift is very small, real lambda, then geometrically you can prove that it's actually the force matrix, and you can connect it with the and so
the last slide. So you said that U is 0.
Here most probably U was not 0. So this is I don't remember, but here I just wanted to show this is still the ground state configuration that I remember, but here I most probably had something some for final. Most probably you want in this case. So that's why you have multiple people. That's why it is. The first method, I will give it there, single particle. The first method I am doing is just for single particle, when you don't know interaction. So you have Heisenberg scaling, and then you need to think of the operator. Because I cannot do state topography, as I said. So I physically cannot calculate, from experimentally cannot evaluate this HRI information. Experimentally, this is very non-trivial. Yes, cannot. So what the best thing I can do is to look into some operator which is called charge density operator. So this is just minus 1 to the power I CI. So minus CI dagger CI is the occupation probability at a given cycle. And you just choose this quantity, and you can see that how this quantity behaves as you change your E. And in this extended phase, where E less than 0, this charge density operator value is 0. Almost 0 as you increase the system size. The system sizes are mentioned there. But in the localized, it has a finite.
So how this operator is connected to RTL?
Connected.
Like in localization, whether a inverse participation, like is it operator connected to that? Because IPL is in the localized space.
See, the quantum mechanical information would be connected to the scaling exponent of, because IPL is connected to the scaling exponent of localization. Right. So now this is not, if this would be the optimal operator, then I would immediately be able to connect it with that scaling exponent. At this moment, it doesn't have any direct connection. Because I can choose another operator. It just has to be experimentally measurable, and I will see how this operator scales. Okay. So now look into this derivative of this. Look into the operator side information derivative that I introduced. How it scales with system size. Scales with system size for different parameter values. And you will see this charge density operator has a scaling of 1.5. So it doesn't saturate to this Heisenberg scaling. It's from L square, but it has a better scaling than that from the short noise, from the classical. So this still offer a quantum and you see it. So this I define in terms of this yeah. So this is the definition. So delta of
divided with the fluctuation.
Yeah. So is the second moment of this operator. Okay. So now this is my single particle result. But the problem is that when you go to multi-particle, let's say you go to a half-filling phase of half-filling, because when you do a multi-particle case, then this actually doesn't have this charge density order in the response, in the ground state response. Because if you see that charge density ordering would be like something like 1 0 1 0 1 0. So particle, there is particle, there is no particle, there is particle, there is no particle. So this is long-range order, this kind of order. And look into this in terms in presence of interaction. This localized phase has no such order. So such order can mostly comes like beyond nearest neighbor interaction and things like that. But at least with the nearest neighbor interaction, there is no such order. So then, if I ask that okay, my charge density wave is not a good operator, and I have multiple particles in my office. What can I do? And then we propose that okay, go beyond radiativity, something dynamic. And the motivation comes from this experimental paper. So actually, it's experimentally very easy to create a box. Experimentally, it's very non-trivial to create any energy. We just can. Ground state you can do. You can approach to the ground state. Any exciting experimentally mostly that. It's a very special concept. But this kind of product steps like in form of box steps, very easy to create. So create a product step like that, and then if you just point it, so this is like to the case, it's above the extended phase or the delocalized phase. Then you will see this at long time, you know. So this is the non-algorithmic localized. So you have started from there. You have noticed final time you have something extended, but due to this initial ordering, throughout the dynamics, it maintains its ordering. That final time. So then, if you look into the charge density wave, and its scale, you will find good scaling. Okay. So this is dynamical system. The idea is that you first prepare a system at some for some initial EI, and do a forward coinching, take it to with some final parameter VA. Do a backward coinching with a final parameter VA plus small shift from that VA plus delta V, and look into overlap between these two states. And in this state, see how it is scaling with time and system size. So now, in addition to system size, time is also a resource. So I'm assuming that we can here have some atomic law, something through which I can very precisely measure time. So if I take advantage of that, then you can think that this is actually along with the system size also time is also a resource. And now look into the scalings. So this is in dynamical context. So we have some. So we start from different kind of initial states. So 1, 0, 1, 0, or the some ground state configurations, and you can see the scalings of this charge density wave. It's n to the power -1, t to the power 6, n to the power -1, t to the power. So with system size, it's extensive, but with time it has some large scale, for some large scale. And these scalings are actually quite universal and very robust. That means if I change my initial states, okay, or point, I am pointing it to the delocalized phase, but doesn't matter that where I am pointing. It can be anywhere. Okay. And every time you will find these scalings. These scalings are quite 2 minutes. Yes. So I have almost finished this thing. Now, if I need to go, then I have to go to a new. I just very deeply that okay, all these things are happening. So we understood that we can build a quantum critical sensors. But if I ask the question, what causes quantum enhancement and critical? So because there are a lot of candidates that happens at criticality, so there is always there is gap closing in second order or standard system. There is this gap system and it becomes gapless. There is usually in second order quantum transition and things like that, some sort of chemical grading is happening. So what is the real reason that this quantum enhancement is happening? And mostly it is argued. There are multiple papers, but I will just highlight one paper that it's argued that okay, it's essentially gap closing. But then we did a work where we showed that it can be. I can get a quantum advantage even if I go and do this maneuvering of my parameters through a gapless line, but it involves some sort of symmetry. So that can also give me quantum advantage. So this is just
possible of finding values.
no. What is it?
Suppose I have like don't energies that the research avoid. So it's not exactly the crossing of eigenvalues. So there you can see that there is divergence of this position. Basically, here one parameter you want to measure, And at this critical point or this profit point, depending on this change, slight change, system response to noise, and that is what we give for safety.
Yeah, but it's always done. For example, if I punch through these gapless, so this is a it has model, so the model is given, and there are two gapless lines. This green line, and there's a red line. So this is this delta, and this is mu. So mu into is a gapless the multicritical part. If you do a parameter element through these gapless line, the Fisher information is always seen. But there is nothing is happening. You are not breaking any similar.
Actually, we have a system where we the Laplace domain and see and what's happening. So we have 4 or 5 or things like proper writing and they move other state levels.
Yes,
And this is the number, and this we can see in the particles. And if this is the particle, the scaling is moved and thing. This dimensions kind of thing. Then it is moved.
so you are saying that the right process.
Yeah, the same because there is an energy process.
Yes,
So there is a change.
yes, because so that's the gap to gap side of it. So if you are saying okay, so now if you actually manage your parameter along this gapless line, what happens when it breaks your symmetry? System is so the number is conserved when you are at this critical point and on this line, but here this number is not conserved. So this is like Kumar kind of exactly about so and then in multicriticality, you have to do some multiparameter estimation, you have to construct this quantification information metric and then matrix, and then you can show this particular quantity in terms of, so this is the total uncertainty which you can write in terms of the matrix elements. And basic idea is that we could show that this quantity G scales like L to the power 6 and should. And we have analytical expressions in the limit L tends to infinity, but delta tends to in the limit delta tends to 0 and mu tends to mu c. That means in the near the multicritical point. And these are the scalings, and we see that this G and F mu, these quantities have a better scaling than Heisenberg. And it's happening my speech paper. Although I am meaning data conversion on the campus. So that's it. Okay. So this is my conclusion. And maybe outlook, one can think out few things that we did hit a roadblock when we wanted to calculate this quantum Fisher information for finite temperature. So it has some singularity. So sometimes this Fisher information matrix can have singularities. Okay, and there is no general strategy for it. And then one can also think about practical constants like true adherence is not possible. So there is some time involved. Okay, and there can be some noise imperfections or dissipations. And if you take into their account, then what happens with scalings? And this multivariate sensing that I defined with this Fisher information matrix and define something that is also not the most right. So from the mathematical point of view, somebody can think about driving tighter bounds. And obviously there are experimental things. So that's it. Yeah. Thank you.
I'm 19 late. Science model and detecting biases. Are you saying that we cannot detect it unless the interaction is beyond that or this? My and can be detected, for example, in the cell of a topological system. And so in the free case, it's too much. Then I introduce interactions. I know that there is this new ordering that will come into the picture, which is charge density. And maybe the topological cases are the mixed with the charge density cases. Can this visual information be a marker to understand those conflicts?
Visual information can be marker of many things. One is that visual is a marker for entire presence of internal business. So that's it. That's very important. Second, if you want to think from the point of view of sensing, then the idea is that find a parameter space to identify some space where systems response is maximum. Okay, and that happens.
Generally, the second order correlation,
Yes.
two particle correlations,
Yeah.
they are always divergent. I mean, not always.
What?
Depends on the order of the conversion. Divergence depends on the order of the conversion.
Yes. So there is something. So you are saying we are minus.
Yes.
So how it diverges.
Yeah.
But yeah, that's
I mean, my
Yes,
question
so
is,
only
in general
second.
context, this can be used as a marker for any kind of order to non-ordering situation, transition, topology.
I would expect.
But the definitions, what we should use, is there a universal definition? It's the quantity direction calculate.
The quantification information is just defined through fidelity subset. Then you always have. Now, fidelity subset is experimentally not very good quality. So we are observable that is the experimental and the charge is something that told this is something that experimentally can do in optical lens because you just need to know what is the local density.
Yes.
What are the local density? No, I prove that now we can they have really the image of the. So now this is something we can really. So what is the you have seen one time advantage you access. So this is not guaranteed. This may vary. We found something which has like quantum advantage to this but it did not saturate the but if there are different system, it may have a different system. Yes, it is more than one or two.
Okay, very interesting. Talk to you.
Now, there will be second initiation there. Now, it's